Not the first part. We breezed through that. It was that second part. When they said, what is the velocity of the rock when it was 25 meters its height? I'll write that.
Is this section different pattern?
When its height was 25 meters. Remember when someone threw a rock and it went like this? So 25 meters, how many times did it hit 25 meters?
Twice.
Twice. So the question asks, what is the velocity of the rock when its height was 25 meters? And they start out by going, on its way up. So there should be two answers to that quadratic. All right, what was the height equation? H equal? Let me look.
15t minus 1.86 t squared.
Thank you.
No problem.
All right. So first the setup. When we started this problem, the first thing we did was, we set 25 for height, right?
Mhm.
It's this. Right here. Quadratic form. We'll set it all equal to 0, right? Remember, I'm going to add this on both sides. I'll subtract this on both sides. I get 1.86 t squared minus 15t plus 25 equals what?
0.
0. Now I'll go to this calculator here. I just want to do quadratic formula. Which you can.
Actually, in my Casio, you can do it too.
Hey, cool! What's that? Those scientific Casios, everyone. The scientific Casios are pretty cool. And they're cheap too, aren't they?
Yeah, oh, like $17.
Yeah, $17. That's some really neat stuff. Alright, let's build it up. I'm gonna use this thing. So clear, let's go up here. I go to y equals, and what do I type in? I didn't want to use t, so I used x. 1.86 x squared minus 15x plus 25. Now, one way I can do this, I can hit the graph, I can use the intersect button, hit enter, 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 and it'll give me my answer. Isn't that cool? That's how fast it'll be. The only thing is, be careful of this. If you want to do this like on Tuesday's test, make a note. If you're going to use the intersect button, guess how many equations you got to have written here? 2. So if you only have one, calculate intersect what? Right? And it won't work. So I need another one. So what is that equation equal to? Go to 0. By the way, you could have done these two equations. Do you agree?
Mm-hmm.
But I always like to make it all equal to 0. So let's go down here and say, all right, equals 0. So this is one technique. Now I hit graph. If my window's out of whack, I hit zoom 6. I hit trace. And I like to get the cursor. Where is it? Follow those numbers. I'll make it zoom in so it's a little bit better looking. There you go, that's a lot better. I want to get my cursor close to it. That's close enough. That way the calculator will run to that 0 right there. Claire,
Wait, is it minus 25 or is it plus 25?
you're the best, is it?
I think it's
Let's see, is it?
plus.
I think it's close.
What I did was, Claire, I added this to both sides,
Okay.
then I subtracted this.
Okay.
And Claire, something else you could have done, I'll be honest. You know how I set this equal to 0 like this? You could have set that as one equation, and that as another one. And it would have done a straight line, but then you'd have to play with the window. Because at y equals 25 is really high up.
Right.
I just like to get it all equal to 0 so my eyes can focus on the x-axis, right?
Yes.
And so I do this, and I hit trace, Claire, and I get it close to the answer. Oh, that's close enough. Now I go to second trace, which is calc. Which one's intersect? 5, hit 5, and I just hit enter, enter, enter. I might have to look. Enter, enter, enter. What's the answer? 2.35, 24952. All right, done. There it is. Now, is that the time when it was on the way up?
Down.
2.35, 34952. Don't focus on the shape of this graph. But Evan, isn't there another answer? Isn't it at a later time? So remember, someone threw the rock like this. It went up and then it went down. So wouldn't that be the time on the way up? Now, if you want to do the one on the time coming down, wouldn't that be the later one? Does that make sense? Cool, great.
If you got like 2.34, that wouldn't make a big difference, would it?
It would. It's going to throw your final answer off a tad. You'll be close to the answer. So that's why you want to use intersect. So you get it accurate to what? All these places. Now here's the great news, when I did all this, maybe you're sitting there going, oh man, I gotta copy this number down, write it down. No. Well-designed calculator here. I'm gonna hit quit, okay? I'm just gonna hit X on my calculator. Guess what it's gonna tell me X is? Isn't that cool? Very well-designed calculator. So it knows when I do that, it's gonna store that number into what letter? X, so then you don't have to worry about what? Copying it down, stuff like that, so it's there. I think I'm done this problem except for one thing. What did they ask? Let's go back. What is the what?
Velocity.
So where do I have to plug this?
As the derivative.
Oh, what was velocity again?
15 minus 3.72 t. What point? How much? 3.72, I guess. 1.86 times 2. How much is it?
Am I right? And then I substitute what? I'm going to stretch it out though, I don't want to round it.
Oh, you have
The
to
rule of
put.
math, I don't round to the final answer. 2.35, 34952. And I plug it in here, so look what I'll do. Watch how I type this on my calculator one. 15 minus 3.72, watch what I do, times what letter?
X.
It'll do that. Cool? Because X is that number. I made sure it was that number. There it is. So the calculator is designed to facilitate this kind of stuff. If you know what, I spent 10 minutes, quadratic formula. Write out all these places, right? And all this stuff. It's there for you. Now, is there a solver on this calculator? There is. I never use it. I solve everything with the graphing tool because you get to see all the solutions. What if a graph hit the x-axis five times? There's 5 answers. Or 2 times, or 1. What if the graph never hits the x-axis? There's no solution, right? So that's why I think it's a great way to approach it. Couple other things to talk about. What if I didn't put that 0? Is there another way to do this? Yep, go up to that menu. What's number 2 say? 0. So if you do this, the only reason I didn't do this first, you gotta hit more buttons, watch. 0, that's an x-intercept. So if I hit this, first of all, I'm going to make sure my trace is near there, my cursor. So I'm going to trace and just get near there again. Come on down. All right, there it is. Close enough, right? All right, second calc, 0. Left bound. You got to make sure your cursor's on the left side of that x-intercept. It is. Hit enter. Right bound. You got to move the cursor to the other side. Then hit enter. Then guess just hit enter. But you notice I had to hit more buttons. I had to look at it before I could just go like this. Right? So I prefer intersect. If you remember, put the equal 0. True? So that's another way to do it. I'm trying to think, anything else? I don't think anybody in here would have to do this, but I might as well show you something. I seriously don't think anybody's ever going to need this button. Ever, you know what Math 8 says?
Derivative.
N deriv. So what if I said N deriv, what was that original function? 15x
Minus 1
minus 1.86 x to the what?
square.
I'm going to put comma x. I just don't think anybody in here is ever going to need this, but I'd like to show it to you for one day. You go, oh, I'm going to use this. I'm going to ask the calculator to take the derivative of this and then substitute for the x that number. Okay? Right? Comma, here we go. What is it? 2.35, 3495 what? Did I get the same answer? I just don't think, wow, whoop-de-doo. Because was it hard to do that derivative? See, did you like that though? It was math 8. Go to math 8. See this is end derivative? I mean, look at it. Oh, you got the update? It's updated? That's fine. Still work. You may prefer it in this mode. Let's see what you got. See it? And you put it all in there, and then here you're gonna have to put the 2.35. But make sure you put what? Put the H equation. So type 15x, I just use that. 15x, yeah, there you go. 15x, don't worry, the x only went off, just gets to be x. So we'll just quit. Yeah, put an x, the x. Oh, cool.
And then here.
Minus 1.868 squared. Oh, whoa, whoa, whoa. Get back in there. Can you left arrow up back in with that thing? Oh, good, good, good.
Oh, okay, so.
Minus 1.86
Square.
squared.
Okay. and
Nice.
then Over here.
In that little box, put, I like your mode.
2 0?
Nope, look at the box, you gotta put in there, the 2 point what?
Oh.
That
X,
whole thing.
X.
He'll let you do it.
X is X.
I don't know if that'll work, but see, that means X was stored as something else. So I mean, it's second arrow, just go back in here, right here. Let's put 2.35, this time we'll manage manually, touch 34952. Right?
Yeah.
Oh, I know what we're doing wrong. It's not 18.6, it's 1.86. Amber, I'm gonna be honest with you. I don't know if you're gonna ever want to use that button because is it hard for you to take that derivative?
No.
Not at all. That's what I mean. That's the only thing it was helping us out with. You're like, oh, big deal. I know how to differentiate that. But what if it was something crazy, then maybe it would be nice. Does that make sense? But if there's anything this calculator does in terms of calculus, I'll show you. Show you anything this thing will do. Cool? Great. So use that solver whenever you want, especially if there's application problems. I'll put that off to the side. I don't think we're going to need that anymore. But if you do have questions about the calculator, I'll be glad to do it. Did anybody have any other questions from 3.7? Position, velocity, acceleration, right? PVA going down. The hardest part might be just dealing with the technology to help you solve some of that stuff. That's it. So, you ready for related rates? Oh yeah, I got a handout. I got a handout on it. Well, let's. You know, look what cycle is in. Not 3.8, it's in what?
3.9.
So when you're like, what, Calc 1, they don't do 3.8? No, they could have. And when you know what the title was? Exponential growth and decay. Our Calc 2 course puts a couple of those problems in there, so they wait till Calc 2 to do it.
Is that the A equals to E0 KT?
That's it. They, for some reason, they wanted to put it in Calc 2 when you learn separable equations, because it flows better. It's not a bad idea.
But that's very interesting though.
It's interesting topics.
Very interesting.
Oh, and if you talk about like
The-
carbon 14, and how you can date artifacts. Like they dated everyone, you know the Shroud of Turin?
uh-huh.
They dated that by carbon dating, back in 1988, by the way. But all that stuff, carbon dating, things of that sort, he's right. Population growth, it's an interesting section. This is related rates. All right. So you'll come back to that 3.8 in Calc 2, once you learn the separable equations. What's related rates? Well, to understand this, so let me just go back to this thing. So we can make sense of this section, related rates. X squared plus y squared equals 9. Do you remember how I said find dy dx? Do you remember what we had to do? We had to use a new technique of I almost said integration, of differentiation.
Uh-huh.
It started with the letter I.
Implicit.
Remember? Implicit. And look at the denominator, what's that letter?
X.
So what we did was, we said in our first step, we'll differentiate both sides of the equation with respect to what letter?
X.
X. Does anyone see why? You might have been, why am I always differentiating respect to X? Because in the denominator, that's the letter X. Cool? All right, so that's why, we differentiate both sides with respect to X. That became a what?
2X.
Became 0. But when we did this, it was almost like, you're not X. You all agree?
Mm-hmm.
So we used chain rule. And you go, how did it work? we put the 2 in front by power rule. We decrease this parentheses y to a first. And then by chain rule, I'll just put this equals 0 over here. Chain rule said always multiply the chain, which was the g prime. So I'm going to say this to myself and I'll write it down. Then I have to here put derivative of that letter with respect to x. Oh, then that would be derivative of that letter with respect to x. But to keep it simple, every time we did implicit, we said just put down a what? D, y, dx. Every time we differentiate y, it makes it easy. True? But that's why. Everyone okay with that? Yeah?
Why did you put the derivative twice? One is y prime, then again.
Oh, that was y to the first.
Okay,
That's really why I don't like to write y prime down.
okay.
Because sometimes that one's invisible. All right, so glad you brought that up because sometimes that one's invisible and that's what confuses a student. So I recognize that to like, I'm not seeing it, I'm like, because there's an invisible one there and I go, oh. So I'll write it, but we know in math, that means what? Derivatives. So every time I do this problem for emphasis, I'll do dy dx and I won't put that one there.
Okay.
Because that did look like a y prime. Someone okay with that? Cool, I did that because what if this was y cubed? It would have been what? 3y to the
2.
second, and this would have still been dy dx. Let me just show you that, look. X squared plus y cubed, this would have been 3y squared, that still stays. Because you go, what's the derivative of that letter? Respect to x. Well, with related rates, everything is with respect to time. So with related rates, over this entire section, I like to spend today and tomorrow. There's not many sections in this book where I do that. Optimization and related rates, Calc 1. Let's spend 2 days on it. Why? Because every problem changes. You're going to differentiate everything with respect to what? With respect to time. And what letter are we going to always use for time?
T.
So no more differentiating